So hopefully you saw in the email that I have a hard stop at 2 today. I have a Zoom meeting that I can't be more than a minute or two late for. I apologize for that. But I'm sure I'll run over occasionally to gain back the time that you get today. A couple of things I wanted to point out from the other day. For example, I wrote down this equation somewhere here as this Rubik's Cube approach for solving the off-resonance rotation. And one thing I wanted to then emphasize here is these rotations are written from right to left. So backwards from English, because it's matrix multiplication. So M0 here is a column vector that's the initial magnetization. So, for example, if we just had Z magnetization, that would be the column 0, 0, 1 to represent the Z. And then RZ minus theta was my first rotation around Z, to bring the phase back to the x-axis, so on and so forth. So right to left rather than left to right. But in the literature, this can be very confusing. So you have to pay a lot of attention when you're reading a paper as to which way the author has written things down. Now, in the picture that I did, I did these rotations one at a time, but of course, these are the matrices for the rotations. So I could plug in and have Mathematica multiply all 3 or 5 of these together. And if I did that for a pulse of phase 0, so with phi equal to 0, just starting with the next pulse, this is the resulting matrix. So if I was programming a computer, I could, of course, just put in the 3 by 3 matrices and let the computer do the multiplication. Or I could put in this matrix where the multiplications are already done. I'll have the first problem set posted sometime this afternoon. Hopefully everybody got an email from Whitney with the link to the Dropbox. It would have been in the email that told you that this room was still broken. I hope.
Yes. Yeah.
Okay, so you should have access now to the PowerPoints, and then I'll put the problem set up as well. Of course, the PowerPoints are getting modified as we go along, so we'll be constantly updating. If you have trouble with the Dropbox link, email Whitney and or me. So here are then just some calculations of the performance of 90-degree pulses and 180s. And you saw the 180 already. Here I'm only showing half because it's symmetric. And basically, as you go off resonance, it doesn't behave very well. In contrast, a 90-degree pulse, so the solid line here is the magnitude of the transverse magnetization. And you can see the magnitude of the transverse magnetization is pretty close to unity for quite a while. Certainly out to an offset equal to the strength of the pulse. You have pretty close to full intensity of transverse magnetization. But down here, the dashed line is the phase of the transverse magnetization. So there's the phase error associated with the off resonance pulse because the magnetization already starts to process as it's rotating from the z-axis during the pulse. The solid line is the total rotation angle, and again, the off resonance rotation angle is always larger than the on resonance rotation angle. On resonance here is a 90-degree pulse. As you go off resonance, the rotation angle increases because the rotation is due to the effective field. The effective field is the vector sum of the offset and the strength of the pulse. The hypotenuse is always longer than the sides. So you rotate off resonance a larger angle. And the important thing you can see here is that you might get to an angle of 360 degrees, right? Here, somewhere in here is 360 degrees at some value of the offset. So there's the B1 field is tilted somewhere, but during the time that you apply a 90-degree pulse on resonance, the off resonance magnetization is going to rotate by 360 degrees, in which case it looks like it comes back to the z-axis, like nothing happened. And that's the cheap way of getting selectivity. Most of the time you're hoping to excite the full spectrum, but sometimes you're not. And that's the simplest way to get some selectivity is to adjust the offset in B1 field. So a 90-degree pulse looks like a 360-degree pulse at some off-resonance position. And one of the problems will ask you to figure out exactly what the relationship is. And then the upper corner here just shows for the spectra what this looks like. On resonance, there's a 90-degree pulse. We have full amplitude. The spectrum is in phase. As we start to move off resonance, the intensity decays initially just a little bit. There's a little bit of a phase error. That phase error gets larger and larger. The amplitude is decreasing. And eventually, when we get to where there's a 360-degree rotation, we don't see any signal. All the magnetization is back on Z. And one of the other things you'll see in the problem set is the phase error, at least in the beginning, is pretty close to linear with the offset. And a phase is always a frequency times the time. So if we have a phase error that's linear with offset, that means we can correct it either with a first order phase correction on the spectrometer or by adjusting some time delay to compensate for that. So that's also a terrific thing about a 90-degree pulse is the most important part of its off resonance effect is a linear phase error. And that's either correctable with a first order phase or by adjusting some times somewhere in the sequence. And again, you'll work that out some in the problems. So then we did most of what I wanted to do in this first section. To remind you, this is what we mean by the Fourier transform. It's our signal multiplied by a complex exponential and then integrated. This gives the spectrum in angular units. The spectrometer normally shows you the result in hertz. So in that case, this complex exponential would be 2 pi nu rather than omega. And that's in theory. The data on the spectrometer is digitized. So you're actually doing a discrete Fourier transform, not an integral. And that turned out to have some important consequences, and we talk a little more about the actual data acquisition has some importance for how the experiment actually gets set up. But we can leave that. Anyhow, then we're back to the 1D spectrum. We talked a little bit about inversion recovery, etc. I'm going to skip over that for the time being and get on to what our real problem is we have more than one spin. And if we just think about the amide hydrogens, if the protein is enriched in nitrogen 15, there's a nitrogen 15 spin connected to the amide hydrogens. There's a 3-bond scalar coupling between the amide hydrogens and the alpha hydrogens that is important. So we have to know something about more than one spin. And for most of what we'll do when we have, say, 3 spins, they're going to be treated at more or less independent couplings. So if we're talking about the amide nitrogen or the amide hydrogen and it's coupling to the amide nitrogen and to the alpha hydrogen, these, for the most part, we can treat them independently of each other, which is a huge simplification, which means once we understand how 2 spins work, extrapolating to more spins is easy. The big exception will be when there are identical spins, like the hydrogens in a methyl group. And then one has to be more careful because the methyl hydrogens are magnetically equivalent to each other, and that means a little bit of group theory has to come to bear. But until we get there, understanding 2 spins is enough. So 2 spins, they obviously both can be in alpha state. One can be alpha, the other beta, vice versa, they both can be beta. And the energies are worked out here. And again, we have the Boltzmann equation to give us the populations of the 4 energy levels. Alpha, beta, and beta alpha may not have the same energy because, of course, the gammas can be different. If the gammas are different, then the omegas are different. So the energy levels are different. They'd be equal to each other if we're talking about hydrogens, in which case gamma would be the same for the 2 of them. So this starts out, relatively simple. Where the interesting part comes in is if there's a scalar coupling or a dipole coupling between the spins. Because now the energies depend on whether the partner spin is in the alpha state or the beta state. In solution, an isotropic solution, the dipole couplings are going to average to 0. So we're only left with thinking about the scalar J couplings. In solids, of course, the dipole couplings are there. And if we use some alignment medium in solution, the residual dipole couplings are restored. The dipole couplings come back, but only to a very weak extent. The mathematics are quite similar between the dipole couplings and the scalar J couplings. So once one learns the mathematics for one, adapting to the other is relatively straightforward. So here are now the energy levels for a positive J coupling. The J couplings can also be positive or negative, and that will swap everything around. But for a positive J coupling, then here is no J coupling, here is with the J coupling, here are the new energies. These are the energies just from the gyromagnetic ratios. Here is the contribution for the J coupling. J's historically are measured in hertz. So to get them into energy units, we need this factor of 2 pi to get the angular units. And then there's the product of the two magnetic quantum numbers. And you can see here in the picture then, whereas the transition energies from alpha alpha to alpha beta, or beta alpha to beta beta are identical if the spins aren't coupled. If they are coupled, the transition from alpha alpha to alpha beta is less energy than beta alpha to beta alpha. And that means here, in the absence of a coupling, our line here, say on the proton, is doubly degenerate. But with the coupling, that line is split into the multiples. This is a bad figure because this line should be twice as big as this line over here. I forget every year to fix it. And similarly, the S spin, perhaps the nitrogen spin, in the absence of a coupling is doubly degenerate just at the chemical shift, but is split into a doublet by the scalar coupling. And with lots of work, careful analysis of all the minus signs, it's possible then to figure out which of these lines is the partner in the alpha state and which is the beta state. And this wasn't so important to people before the Troisi experiment, and then it became important. So for the amide hydrogen and amide nitrogen, this is the hydrogen whose nitrogen partner is in the beta state. This is the hydrogen whose partner is in the alpha state. And the same thing here. This is the nitrogen whose attached hydrogen is in the beta state. And this is the alpha state. Now you might think these lines shouldn't be drawn the same height because the alpha and beta states are populated differently. There's more nitrogens in the alpha state than in the beta state, for example. But that difference, as we said, is very small, on the order of 10 to the minus fourth. So we don't see it. It looks to us like they're equal to each other. And our difficulty then is now to expand our mathematical tools to cover this more complicated system. Yeah.
So the J coupling originates from shared electron density.
Right. So in the covalent bond, let's just take the simple case of the amide pair. So if we have a hydrogen spin in the alpha state, the electrons are also spin 1/2. So there's 2 electrons in the bond between the hydrogen and the nitrogen, and they're paired. So one is alpha and one is beta. But because if the hydrogen is in the alpha state, the electron that's in the beta state has a slightly higher probability to be near the hydrogen. And that means that the electron in the alpha state is more likely to be near the nitrogen. And that's going to make it a little more favorable for the nitrogen to then be in the alpha state. And this also switches around. The probabilities are low, so the J couplings are on the order of tens of hertz, but our lines are narrow. So it's basically that each spin has a tendency to polarize the nearby spin. And this is why it gets weaker as you get more covalent bonds. So to get to the 3-bond coupling between the amide hydrogen and the alpha hydrogen, the hydrogen, the amide hydrogen in the alpha state has to polarize the bond a little bit between the hydrogen and the nitrogen. That has to polarize the bond a little bit between the nitrogen and the carbon, and that has to polarize the bond a little bit between the carbon and the alpha hydrogen. So as a result, and how strong the polarization effects are also depend on the gyro-magnetic ratio. So it's different if you have to pass through the different heteronuclei. But anyway, it gets weaker for obvious reasons. And as a result, the one bond coupling, for example, between the nitrogen and the amide hydrogen is about 92 hertz. But the coupling between the amide hydrogen and the alpha hydrogen depends on the dihedral angle, but maximally it gets to be about 12 hertz. So more or less an order of magnitude smaller because of the relay through the multiple bonds.
Would there ever be an instance where it's the other way, like it's more likely that the two spins are the same, both alpha, both beta?
Right, well, that's going to be a little bit higher energy. And that's why these energy levels shift relative to each other.
Yeah, I guess I'm wondering, like, is there, how would the J coupling be the opposite side?
Oh, then just what we think of as, here I said that this is the partner in the beta state. And if the coupling was negative, that would just be the alpha state, and the other one would be the beta state.
Yeah, but like, what's the physical, like, how does that happen physically?
Oh, why is the J coupling positive or negative?
Yeah.
And may talk about that. That has to do with the quantum mechanics of magnetic field gradients at the nuclei. So a little complicated. And off the top of my head, I don't remember the equations. But the equations are known. All right, so that's just a justification as to why we have to move on. And that will take us, hopefully, to starting to think about the quantum mechanics of all of this. And it's always a bit curious to me because the experiment is happening on 10 to the 17th spins. So the quantum mechanical effects are basically negligible. For example, in quantum mechanics, you aren't allowed to measure Ix and Iy at the same time. There's an uncertainty relationship between it, but we do it all the time. That's how the spectrometer measures the signal, because the quantum effects are scaling down with the number of spins, and we just have an enormous number of spins. Nonetheless, the formalism that comes out of the quantum mechanics is the clearest way to explain the experiment. Off we'll go. We'll go through some formal bits, but of course, we'll eventually get to a formalism that looks quite a bit like the block equations, in which case, for most problems, you can forget all the complicated quantum mechanics that got you to this final formalism, but this may be the one time in your life you see it. We'll go through. And we have to remember that for us, quantum mechanics is going to be a recipe for calculating the NMR spectrum. Now, there are other things about quantum mechanics one can be interested in, but we're only interested in the part that says, what's a recipe for calculating the NMR spectrum? So there's always something you have to take on faith. So on faith, we'll say this is the Schrodinger equation, foundation of quantum mechanics. In NMR, we mostly work in hertz, so h bar will disappear. So we work in units where h bar is equal to 1, or if you like, we think of energies as frequencies. And if you want to get real energies back, given the frequency, you have to multiply by h bar. There's also, as you've already seen, a lot of KTs floating around because of the Boltzmann equation. And mostly we're not going to write those down either. So given some answer in the calculation of quantum mechanics, if you want to know the real number, one might have to look at the units and figure out from units analysis where do I have to put in h bars and KTs to get something scaled to the real world as opposed to a simple world where all these factors don't have to be written all the time. And then the wave function is what we would like to know. And to know it, to solve this differential equation, we have to know h. And h is called the Hamiltonian. And for us, it's going to consist of the Hamiltonian for the static field for B naught, the Hamiltonian for any of the RF pulses that we apply, and then some local magnetic interactions that, for example, are the chemical shift and the J coupling, and might include dipole couplings, etc. So it's a relatively simple Hamiltonian relative to, what optical spectroscopists have to deal with. The wave function, if we could figure out what it was, has an interpretation that the product of the wave function times its complex conjugate is the probability of finding our system in some particular state at that particular time. Normalized wave functions integrate to 1 because the probability of anything added up over all possibilities has to be 1. That said, many of the things that we use in NMR aren't normalized to 1 because that just introduces a whole bunch of inconvenient factors of square roots of numbers. So what's important to us generally is everything is going to be normalized to the same number, which may or may not be 1. And if we need to, we can always renormalize. But having everything normalized to the same number is important. And if need be, we can always normalize as shown here. If this integral wasn't equal to 1, if we take its square root and divide everything by it, then we will end up normalized. And then if this Hamiltonian is independent of time, there's an important result that says that the solution can be factored into a part that just depends on coordinates of the system and a part that depends on time and energy. And E over h bar is a frequency. Frequency times time is a phase. So for a time independent Schrodinger equation, we just have a function of kind of physical variables and then a phase factor. This defines the energy as shown here. And this tells us something that's going to be important throughout is given a time-dependent problem in NMR, we're going to try to find a transformation to a frame where the problem is independent of time, because then we know how to solve it. So this idea already becomes very important. H is called an operator in mathematics. It operates on a function to generate a new function. And if you've never seen an operator, one you know something about is the derivative with respect to x. So if A, and most of the time in the class, operators will be scripted or bold-faced. So if A is the operator, A operating on some function is just its derivative. And we can have all sorts of operators. In our case, all the operators are going to be linear, which is convenient, which means if you operate on the sum of two functions, then the result is the operator on the first function plus the sum of the operator on the second function. Or if you multiply a function by a constant, the result of the operation is just the constant times the operator acting on the function. Just like derivatives. Right? Derivatives, you know the sum rule for derivatives. It'll also be important that some functions and operators have a special property. So here, if our function is the exponential function, and we operate with the derivative and apply the rules of differentiation, the derivative of e to the lambda x with respect to x is lambda times e to the lambda x, which is lambda times the original function. So if we have an operator that operates on some function and it gives back a constant times the function is called an eigenfunction of the operator. So the exponential is the eigenfunction of the derivative operator. Cosine is not an eigenfunction. Right? If you take the derivative of the cosine with respect to x, you get back negative of the sine. You don't get back cosine. So the operation is perfectly allowed mathematically. It makes perfect sense, but it's not an eigenfunction. Cosine is not an eigenfunction. And again, it'll turn out that functions that are eigenfunctions turn out to be really important in all of quantum mechanics. Again, our goal is to measure things, and that means that measurable quantities in quantum mechanics are associated with operators that are Hermitian. And this is an integral definition of what a Hermitian operator is. We're going to very quickly in NMR deal with matrices, and it's much easier to understand. A Hermitian matrix has the property that it's equal to the transposed complex conjugate of the matrix. So that's kind of indicated here. The same thing as this integral, but the integral is more complicated, so you can forget about it. If we have a matrix representation of an operator and its complex conjugate transpose is the same as the operator, that means it's Hermitian. And we'll see examples of both. Why this is all important is, again, we want to measure something, and quantum mechanics says the way you measure something is to do this integral. The operator acts on the wave function that generates some new function. It's multiplied by the complex conjugate of the original function, and you integrate, and the result is what's called the expectation value, for us the result of a measurement. In quantum mechanics, it means the average of the result for a large number of identically prepared systems. And we'll have to generalize that notion very quickly. Just another piece of mathematics that'll come up over and over again is if we have a Hermitian operator, their eigenfunctions are orthogonal. in the sense that if we multiply, if we have two of them here shown by I and J, if we take the complex conjugate, do the multiplication, the result is the Kronecker double. If it's the same function, we're integrating the probability and we get 1. If they're different functions, we get 0. And another factor of Hermitian operators is that they form a complete set, which means that any well-defined function in whatever that space is can be written as some linear combination of the eigenfunctions. And to give you just an example, I'm going to skip over this for right now. This is just a formal way of finding the coefficients in the expansion. But here I've just done a simple example. Sines and cosines, you probably know, are orthogonal functions for doing Fourier analysis. And so here in blue is some quadratic function that I just made up. And here are the first two sine functions. Here's one lobe, here's a full lobe. And here is how good the agreement is if I optimize some coefficient just using the first lobe of the sine function. And you can see it's not very good. And then I pick the first two lobes and optimize the coefficient, and things are better. And if I take 5 sine functions and optimize them, now you can see the agreement is very good. And the business with Hermitian operators and its eigenfunctions says that we're guaranteed to be able to do this. If we take enough terms, we're going to be able to reproduce any function that's well defined on that space. And that also will turn out to be an incredibly powerful idea. So it's a generalization of Fourier analysis for more complicated spaces. I'm going to get tired very quickly of writing size. And Dirac came up with a shorthand in which we just indicate the nth wave function by this symbol with the vertical bar, some quantum number, and then this angle bracket. And this was, he called the cat. So for example, the wave function alpha, instead of writing psi alpha, I can just write bar alpha bracket. And then the complex conjugate is written the other direction, which he called the bra. So if you put them together, that's the bracket or the bracket, and that means integrate. And then this, the result of this integration shown here, what would be, if these were eigenfunctions, they'd be orthogonal, and we would get 0 unless phi and psi are equal to each other. So this shorthand is very convenient. And then my properties of the eigenfunction says if I have a collection of eigenfunctions described by n, then I can take a linear combination of them and represent some arbitrary function called psi. And then here's the recipe for finding the coefficients. The nth coefficient is found by pre-multiplying by the bra m and then doing the integral. And because of the orthogonality, everything will cancel except for the nth one. So we'd be done, except for we don't have a collection of identically prepared states. Our 10 to the 17th states in an NMR tube have to satisfy the Boltzmann distribution. So we need to generalize this idea to having a Boltzmann distribution. But of course, gotten one slide ahead of myself. So here, back up a bit, here's the expectation value. And in Dirac notation, this would be written this way. And then I can expand these wave functions into two series by the double summation over m and n, in which the m goes with the bra, so it has the complex conjugate of its expansion coefficient, and the n goes with the ket. And I've written them backwards here because I know what's coming next. And I imagine then this is something with two indices. So I imagine that it's a matrix. And I want it to be a matrix that came from some operator acting on a wave function. So I invent this operator P that's called a projection operator. And here I have, this is the matrix representation of the operator. And now I have two matrices multiplying each other. So I can collapse the sum by the laws of matrix multiplication. And I end up finding that this is all equal to the sum of the diagonal elements of the product of these two operators. And the sum of the diagonal of a matrix is called the trace of the matrix. So in the Dirac notation, the expectation value, what we want to measure, is obtained as the trace of the product of this projection operator times the operator of interest. And now we want to generalize this for the fact that we have a Boltzmann distribution, and this picture turns out to be very convenient for doing that generalization, because we're just going to try to average over a Boltzmann distribution. So here the horizontal bar means average over the Boltzmann distribution. So then I need to know the probability, the Boltzmann probability here of each state of the system. Each wave function now has a different probability in order to satisfy the Boltzmann distribution. I substitute in what I just wrote down. Given a set of functions, m and m, the bras and kets, and given the wave function, this part is independent of the Boltzmann averaging. The Boltzmann averaging just affects the relative weighting of the different contributions in this summation. And that means that this average just gets applied to the coefficients as shown here. And now I'm going to call the average of the coefficients, which is the average of this matrix representation of the projection operator. I'm just going to call all of that the density operator. And the density operator then has a matrix representation just like this. And now my ensemble average expectation value, what I'm actually going to measure on the spectrometer, is the trace of the density operator times my operator of interest, whatever my measurable is going to be. And the trace is independent of the order of the multiplication, so I can think of it either way. So if you like, I could think of my theory starting here. I have an expression for an observable, I can ask my physics friends, what's my observable for an NMR spectrum for a free induction decay? What I need then are rules for how sigma evolves in time. What is sigma when I start at Boltzmann equilibrium, because that's where I start the experiment. And then when I apply pulses, how does sigma change in time? And then what happens to sigma when I detect the free induction decay? Well, that's all I need to know. So we have to convert the Schrodinger equation into an equation for the density operator. And we start by writing the Dirac expansion for the wave function as shown here. And you can kind of see what's going to happen. First, I'm going to multiply both sides by a bra and then make use of orthogonality to end up with an equation now for the expansion coefficient. And this would be a very large number of different differential equations. I have one different differential equation for each value of k. So I'm going to have a big system of differential equations to solve. But now I can come back and then ask, what does this look like? This is the derivative of the average of the product of CK and C star. That was my definition. I have to apply the usual chain rule of calculus. And now I can substitute what I just calculated for the average of the derivatives. I substitute that in. I play around for a while with the algebra, and I'll leave that to you. But I can put this in the form now that the time derivative of the density operator is minus I bracket H gamma sigma bracket. And this bracket means the commutator. So the bracket means H times sigma minus sigma times H. Hopefully, no, I didn't write that down anywhere. So I'll try to add that to the slide. So in quantum mechanics, these square brackets mean the difference between the products going in one sense and the other sense. So that's our rule. So that will let us propagate sigma if we know H. And then we just need to know sigma for Boltzmann distribution. And in principle, we can then figure out what sigma is at any moment in time. Now, we started with the Schrodinger equation, and I told you had to take that on faith. I could have said, let's just start with the Liouville von Neumann equation. You can take that on faith because they're the same equation. One is just averaged over a Boltzmann distribution. Either one is as good a starting point. So if you don't like the derivation that we did to get this point, you could just say, written on a stone tablet somewhere is the Liouville von Neumann equation. And that's our start in analyzing the quantum mechanics of a thermal ensemble, an ensemble that has to satisfy the Boltzmann distribution. And again, just like we had an answer for the Schrodinger equation that the Hamiltonian was independent of time, we have an answer for sigma if the Hamiltonian is independent of time. It's just the exponential of the minus I Hamiltonian t sigma exponential I Hamiltonian of t. So again, if we can find a frame where the Hamiltonian is independent of time, we know how to propagate the density operator forward in time, and then we can undo the transformation and then calculate our observables. Now, here we have the exponential of an operator. The operators can be represented by matrices using this Dirac notation. So we have the exponential of a matrix, which you might not have encountered before. But anytime we're uncertain about the mathematics, we can try to figure out what the math means, usually by doing a Taylor series expansion, and then trying to figure out term by term. So here, the exponential of the operator is written by Taylor series expansion. And again, in general, I have to pay attention about commutation of matrices. Operators are matrices. Matrices don't always commute, but a matrix commutes with itself. So I can here take, if this is the answer, I can take the derivative of both sides using the chain rule, being careful not to commute anything. A common trick that I probably used here. Is that H commutes with its own exponential, because when I do the expansion here, H will commute with the identity operator and it'll commute with itself. I can move this H around and eventually show that this derivative, in fact, gives this result. So this is the solution if H is independent of time. I want to talk about this today. I think in interest of time, I'll let you take a look at this map over the weekend and just say, of course, we're going to want to do transformations. You've already seen that. So we have to know what happens to the Liouville equation if we transform to a new frame. And the slides that I skipped give the answer. So if we have a transformation, the transformation is going to be represented by this operator U. For us, the U's are going to have the property of being unitary. And this will mean that their complex conjugate transforms will be the inverse rather than being identical. So a Hermitian operator is complex conjugate transform, usually called the adjoint, by the way, is itself. So it's self-adjoint. A unitary transformation, its adjoint is its inverse. This makes a lot of sense. For example, a rotation, if you look back at those rotation matrices, their transpose inverses give you the negative rotation, which is what you expect. If you rotate one direction and then rotate the other direction, you should come back to where you started. So a lot of our transformations are going to look like rotations. After all, we're doing NMR. But they might be time dependent. You here might be time dependent. And in that case, we end up with a density operator in the new frame obeys a commutator with a new Hamiltonian, and the transformed Hamiltonian depends both on transforming the Hamiltonian with the unitary operator, but also depends on what the time derivative of that operator is. So if we have a fixed rotation, that's going to be zero, that's simple. But if the transformation is time dependent, there is going to be some new contribution to the apparent Hamiltonian. And that's really important to us because that's in fact how we're going to try to get rid of the real time dependence in the Hamiltonian. This is why the rotating frame transformation works, is that this will end up being the part that compensates for the 500 megahertz rotation, for example. So part of the game, faced with some time-dependent Hamiltonian, is trying to figure out a U such that this combination becomes independent of time, and then you know how to solve the problem. So I've justified this, the justification of this equation, of course, is on the earlier slides. You can look at that over the weekend, and that's where we'll start up. And at that point, actually, we have the equations we need, and now the problem is how to use them. Any questions? And again, we have to end early today. I apologize. Few students ever complain about ending class early. Any questions online? Again, you should have the Dropbox link now to the slides, and I'll get the first problem set posted later today. And we'll see everybody on Wednesday. That gives you plenty of time to think up questions. Everybody's good? And if you're uncomfortable with matrices, and everybody gets a squeamish feeling with matrices, I'll upload a help sheet for math review you can look at. Hopefully for you two, a lot of this looks familiar.
Yeah.
You get the codes for a little while.
Thanks.
Yep.
Have a nice weekend.
Great. Just a heads up.
Yes,
We're coming back together.
we are.
Yeah.
Okay,
Yeah.
right?
Yes. There is this. I think I sent an email earlier about talk